Hello, and thank you for joining. My name is Derek Kane, and today we're going to talk about the topics of linear regression and ANOVA concepts. This presentation is one part of a broader series of lectures diving into topics of predictive analytics, machine learning, and data science. The overview of topics we're going to get into today will include a brief introduction to regression analysis. We'll talk about ordinary least squares, and particularly some of the assumptions underpinning the models and detecting the violations of these assumptions. I'll talk a little bit about interaction terms in a model, and then I'll also walk into transformations of the model, talking about level, log, and log transformations. Then we'll move into the topic of ANOVA, and finally we'll walk through a couple practical examples showcasing the techniques of regression analysis being applied. We'll start with a real estate example, and then following that we will get into an example from a supermarket marketing concept, which really brings together a lot of different analytical techniques to solve very common business problems. Without further ado, let's begin. Regression analysis is the art and science of fitting straight lines to patterns of data. Regression analysis is widely used for prediction and forecasting, where its use has been substantial overlap with the field of machine learning. In a linear regression model, the variable of interest is the dependent variable is predicted from a single or multiple group of variables, which we call independent variables, using a linear mathematical formula. Regression analysis is also used to understand which among the independent variables are related to the dependent variable and to explore the forms of these relationships. We went through the topic of EDA in great detail in a previous lecture, and it also talks about these relationships. So if you're looking to understand more about detecting these patterns, feel free to go back and review that presentation. The earliest form of regression was the method of least squares, which was published by French mathematician Adrien-Marie Legrand in 1805 and by German mathematician Gauss in 1809. Legrand and Gauss both applied the method to the problem of determining, from astronomical observations, the orbits of bodies about the Sun, mostly comets, but also later than the newly discovered minor planets. In the 1950s and 1960s, economists used electromechanical desk calculators to calculate regressions. Before 1970, it sometimes took up to 24 hours to receive the result from one regression. This is something that we take for granted, even though the technology and the approach of regression analysis has been around for a couple centuries now. But the computing power and the resources required to get business-level insights from regression, only recently have we stepped into computing power that can handle these tasks. On the right-hand side, we have a nice picture, which is the first published picture of a regression line by Francis Galton in 1877. So, for the historians out there who are interested in the evolution of regression and econometrics, this is the first time a regression line has ever been seen in a publication. Many techniques for carrying out regression analysis have been developed. Familiar methods such as linear regression and ordinary least squares regression are parametric, in that the regression function is defined in terms of a finite number of unknown parameters that are estimated from the data. Non-parametric regression refers to techniques that allow the regression function to lie in a specified set of functions, which may be infinite dimensional. Our focus will be on ordinary least squares regression and parametric methods. So if you're interested in exploring regression analysis at a much deeper level beyond the scope of what we're talking about here, feel free to actively seek out through Google searches and through literature what information is available. There's a wealth of knowledge out there, but due to just the sheer magnitude of this subject, we're going to focus on OLS regression. Regression analysis may be used for a wide variety of business applications, such as measuring the impact on a corporation's profit of an increase in profits, understanding how sensitive a corporation's sales are to changes in advertising expenses, seeing how a stock price is affected by changes in interest rates, calculating the price elasticity for goods and services, litigation and information discovery approaches, total quality control analyses, so Six Sigma or Kaizen philosophy draws heavily from regression analysis. And this can even be applied in human resource and talent evaluation as well. So regression analysis is a very versatile tool with many applications. And we can also use it for forecasting purposes. So a regression equation may be used to forecast the future demand for a company's products, for example. A simple linear regression model can be represented as follows. Y equals beta naught plus beta 1 x1 plus the error term. Y in this case is what is referred to as the dependent variable. That's what we're trying to solve for. We have other variables that we think relate to the dependent variable, and these are called the independent variables, and that's the x1. The beta 1 is what's called a coefficient, okay, and this is used in tandem with the independent variables to help calculate the relationship to the dependent variable. Beta naught is another coefficient in and of itself, but it is commonly referred to as the intercept. And finally, we have what's called the error term. And traditionally, when you see a regression formula being written out, you don't see the error term. But when we make a prediction, it very rarely matches exactly the value of the observed y. So we have a prediction that the formula produces, and we have the actual value, and the error term is the difference between those two. And what's interesting about the error term is it's flexible and dynamic depending on what observation in a data set that we're looking at. Okay, so it's not just like the error term is equal to 3.2 universally. It's dynamic. The output of a regression analysis will produce a coefficient table similar to the one that is being produced below. So in this table, we have our intercept term and our height term. We have a value for the coefficient. We have some statistical assessments in terms of what the standard error is, the t-value, and the probability. And interpreting this table, we know that the intercept is a minus 114.326, and the height coefficient is 106.505 plus or minus 11.55. The way to interpret this is that for each unit increase in x, we can expect that y will increase by 106.5. Also, the t-value and the probability indicate that these variables are statistically significant at the 0.05 level and can be included in the model. So we want lower p-values. So anything that is 0.05 or less generally is considered to be statistically significant. A multiple linear regression is essentially the same as a simple linear regression, except for that there can be multiple coefficients and independent variables. The interpretation of the coefficients is slightly different than in a simple linear regression. Using the table below, the interpretation can be thought of And for each 1 unit change in width, increases y by 94.56. This is while holding all other coefficients constant. And that last statement is the important one. So as we're changing the value for one variable, so for each 1 unit change in width, y is increasing by 94.56, holding everything the same. Well, what is ordinary least squares, or OLS as we're calling it? In statistics, ordinary least squares, or linear least squares, is a method for estimating the unknown parameters in a linear regression model. The goal of OLS is to minimize the differences between the observed responses in some arbitrary dataset and the responses predicted by the linear approximation of the data. So if I produce a straight line to fit the points at the top, I notice that not all of the points lie cleanly on the line. So the distance between the line and the point is the error term. And the goal of OLS is to find a line that minimizes the error terms. Another way we can look at ordinary least squares that helps to kind of fortify the concept is through the following image. Visually, we can look at the distance between the regression line and our data points, and particularly the errors, and we can draw a square that matches from the data point to the line. So all of these different errors have squares of different sizes. If we take all of these squares and we add them up into a total sum of the areas, we get a certain value. The goal of ordinary least squares is to create a square of the smallest size. So what is the regression line that I can put through the data points that minimizes the size of this square? And that's ordinary least squares in a nutshell. There are a number of classical assumptions which must hold true if we're able to trust the outcome of a regression model. I can't tell you how many times that I've seen financial analysts, entry-level analysts, show me regression models, and they say, oh, I've developed this equation that measures this phenomenon. And when you look at the regression model from a data scientist's point of view or a statistician's point of view, we need to ensure that the model is rigorous enough to stand scrutiny and actually is observing the phenomenon that we're looking at. And to do so, we have to make sure that certain assumptions hold true. We need to make sure that the sample is representative of the population for the inference prediction. The error is a random variable with a mean of 0 conditional on the independent variables. The independent variables are measured with no error. The predictors are linearly independent, which means that it is not possible to express any predictor as a linear combination of the others. The errors are uncorrelated. That is, the variance-covariance matrix of the errors is diagonal, and each non-zero element is the variance of the error. The variance of the error is constant across observations. So the principle of homoscedasticity. Consequences of using an invalid modeling procedure include, the consequences have a tremendous impact on the theory that formed the basis of investigating this aspect of human nature. When we decided to build a predictive model, we have our theory. And if we're not building our theory on factual information drawing from statistical techniques, we have a tremendous impact. A lack of linear association between independent and dependent variables, model misspecification, etc., insinuates that we have the wrong theory. So, we might think we understand a phenomenon, but maybe we just have the wrong theory. If we have biased, inefficient coefficients due to poor reliability, collinearity, etc., it leads to an incorrect interpretation regarding our theory. We might have a sound theory, But if the statistics are not significant underneath and our parameter estimates are off, we're not interpreting our theory correctly. Outliers imply that we're not able to apply our theory to the entire population that we're drawing our data from. So outliers have an interesting impact that if our model can't address the outliers, our theory isn't generalizable. And overfitting implies that we're overconfident with our theory. We might have a model that fits the data perfectly in the training set, and we talked about this in the EDA presentation. But if we can predict with high accuracy on the training set, and then when we apply it to new data in our test set, and our test set has very poor predictive performance, well, then we're overconfident in our theory. There are a number of statistics and diagnostic tests we can draw from to evaluate linear regression models beyond EDA. Some of them include, and this is not an all-inclusive list, is the coefficient of determination, residual plots, the Bruce-Pagan or White test. We can look at VIFs or variance inflation factors, influential observations, leverage points, Cook's distance, etc. And I'm going to get into these topics in detail in the upcoming slides. The coefficient of determination, or R squared, is a measure of the goodness of fit for a linear regression model. It is the percentage of the dependent variable variation that is explained by a linear model. So the R squared is the explained variation divided by the total variation. R squared is always a number between 0 and 100%. 0% indicates that the model explains none of the variability of the dependent data around its mean. 100%, on the other hand, indicates that the model explains all of the variability of the dependent data around its mean. Now that we have a sense for the R squared metric, we know that a value of 1 is very good. It explains all the variability, so then that implies that an R squared of 0 is bad. So a question that I'm regularly confronted with is, what is a good R squared value? And more importantly, are low R squared values inherently bad? Well, the answer is no, it's not. And I'm going to talk about why this actually is the case. There are two major reasons why it can be just fine to have low R squared values in your predictive model. In some fields, it is entirely expected that your R squared values will be low. For example, any field that attempts to predict human behavior, so behavioral sciences such as psychology, typically have R squared values lower than 50%. Humans are simply harder to predict than, let's say, a physical process. So if I'm trying to understand a mechanical process in a very controlled environment and develop my regression formula to model this, I would expect to have higher R squared values. However, if I'm using regression analysis, trying to understand subtle nuances of the human condition, well, less than 50% is okay. Furthermore, if our R squared value is low, but we have statistically significant predictors, we can still draw important conclusions about how changes in the predictor values are associated with changes in the response value. And this is also important to understand because creating a model and just predicting the outcome is just one aspect of predictive analytics and data science in general. What the values of the covariates and what they mean in business context are also very important, and we can derive value of those coefficients even though our R squared value is low. Regardless of the R squared, the significant coefficients still represent the mean change in the response for one unit change in the predictor while holding other predictors in the model constant. Obviously, this type of information is extremely valuable. Well, the number of independent variables in your model will increase the value of R squared despite whether the variables offer an increase in explanatory power. To combat this issue, we should focus on utilizing the adjusted R squared metric, which penalizes a model for having too many variables. Well, how many variables should we have in a model? That's another question that I've been pondering lately. And there is no generally accepted technique for relating the total number of observations in a data set to the number of independent variables in a model. There was one possible rule of thumb suggested by Good and Hardin, and that is the following, where capital N is the sample size, small n is the number of independent variables, and m is the number of observations needed to reach the desired precision if the model had only one variable. So for example, if I have a data set that has 1,000 observations and the researcher decided that 5 observations are needed to support a single variable, then the maximum number of independent variables that the model can support is 4. This isn't a definitive rule, but if you're wondering, how many variables should I have in my model, this is one technique that you can employ that helps to guide you in that direction. There are some key limitations of R squared that need to be understood. R squared cannot determine whether the coefficient estimates and predictions are biased, which is why we must assess the residual plots. R squared does not indicate whether a regression model is adequate. As we discussed before, you can have a low R squared value for a good model, or a high R squared value for a model that does not fit the data. Okay, so it's a little misleading in that sense. The R squared in your output is a biased estimate of the population R squared. And so that is another limitation of working with the coefficient of determination. We talked about residual plots in our EDA analysis prior to this, but I want to get into them again. So a residual plot is a scatter plot of the residuals, which is the difference between the actual value of y and the predicted value of y against the predicted value. A proper model will exhibit a random pattern for the spread of the residuals with no discernible shape. Residual plots are used extensively in linear regression analysis for diagnostics and assumption testing, and we're going to get into some of this assumption testing. For example, if the residuals form a curvature-like shape, then we know that a transformation will be necessary, and we can explore some methods like the Box-Cox transformation. So how the pattern of these residuals give us clues in how to work with the data. We will now talk about the concept of heteroscedasticity. Linear regression analysis using OLS contains an assumption that residuals are identically distributed across every x variable. When this condition holds, the error terms are homoscedastic, which means that the errors have the same scatter regardless of the value of x. When the scatter of the errors is different, varying depending on the value of one or more of the independent variables, the error terms are heteroscedastic. A review of a scatter plot of the studentized residuals against the dependent variable can be used to detect if heteroscedasticity is present. The residuals will appear to fan outward in a distinct pattern. And the graph that I'm showing on the left-hand side is showing this distinct fanning out pattern of the residuals. And this is a telltale sign that you have heteroscedasticity. Heteroscedasticity has serious consequences for the OLS estimator. Although the OLS estimator remains unbiased, the estimated standard error is wrong. Because of this, the confidence intervals and hypothesis tests cannot be relied upon. The Baruch-Pagan test, or the Y test, is a method that can be employed to identify whether or not the error variances are all equal versus the alternative hypothesis that the error variances are a multiplicative function of one or more variables. The results of this test show that the chi-squared value is fairly low, which indicates that heteroscedasticity is probably not a problem. There are a number of techniques that we can use to correct for heteroscedasticity. We can respecify the model. Maybe there are variables that we need to include that will correct the condition. We can transform the variables. Maybe a variable transformation technique is required to reduce it. And another alternative is to use weighted least squares regression in place of OLS regression. In statistics, a QQ plot, which stands for quantile-quantile plot, is a probability plot, which is a graphical method for comparing two probability distributions by plotting their quantiles against each other. A QQ plot is used to compare the shapes of the distributions and provides a graphical view of how properties such as location, scale, and skewness are similar or different in the two distributions. If the quantiles of the theoretical and data distributions agree, the plotted points fall on or near the line y equals x. This can provide an assessment of the goodness of fit that is graphical rather than reducing it to a numerical summary. So I want to talk a little bit about this graph right here. So if we're looking at this graph on the bottom left-hand side, we see that the data points aren't touching the line that's cutting down the middle, the red line in the middle directly. They kind of curl to the bottom. Then we have a number of data points that exist on or near the line. And then when we get towards the top, then we see data points that kind of curl up and away from the line. So these quantile-quantile plots are going to show patterns that are very similar to this. Well, what does each pattern mean in layman's terms? So if all but a few points fall on the line, well then that tells us we have outliers in our data. If the left end of the pattern is below the line and the right end of the pattern is above the line, then that's telling us we have long tails at both ends of the data distribution, which I think is the case of what we see with this particular chart. If the left end of the pattern is above the line and the right end of the pattern is below the line, well then we have short tails at both ends of the data distribution. If the curve pattern with the slope is increasing from left to right, well the data distribution is skewed to the right. If we have a curve pattern with slope decreasing from left to right, well then the data distribution is skewed to the left. Finally, if we have a staircase pattern, then the data has been rounded and is more than likely discrete. The concept of multicollinearity is an important one to understand with the regression diagnostics. Collinearity is the undesirable situation where the correlations among the independent variables are strong. In some cases, multiple regression results may seem paradoxical. For instance, the model may fit the data well, have a high f-test, even though none of the x variables has a statistically significant impact on explaining why. How could this be? How can I have variables that aren't statistically significant taken independently, but then collectively as a whole offer explanatory power? To me, that is a telltale sign that you have collinearity. Well, this is possible when the two x variables are highly correlated. They both convey essentially the same information. When this happens, the variables are collinear and the results showcase multicollinearity. Well, why is multicollinearity a problem? Well, multicollinearity misleadingly inflates the standard errors of the coefficients. Thus, it makes some variables statistically insignificant while they should be otherwise significant. And I think one way to think about multicollinearity is imagine you've got a sing-off between Aretha Franklin and Whitney Houston. So they're both divas, they are singing their hearts out, and they're singing the same tune, but they're kind of screaming over each other. Well, when this happens, it's hard to tell which person is singing what. They kind of offset each other and they interfere. And that's essentially what multicollinearity is doing. How can we detect multicollinearity? Formally, we can use a test, a measurement of the variance inflation factors, or VIF, to measure how much the variance of the estimated coefficients are increased over the case of no correlation among the x variables. If no two x variables are correlated, then all the VIFs will be 1. If we have a VIF for one of the variables that is at or around or greater than 5, then collinearity is associated with that variable. Now, I use the number 5 in this case. There's no steadfast rule. I've seen individuals use the number 3. I've seen 6 used for VIF. So I think as we're working with our data set and throughout the types of problems that we're working on, you will find a range that is suitable for your needs, and you can draw from this when running these diagnostic tests. So I think the easy solution here is if I have 2 or more variables that have a VIF around or greater than our threshold, in my case it's 5, one of these variables should be removed from the regression model. To determine which one is better to remove each one individually, and then select the regression equation that explains the most variance or has the highest r-squared value, and keep that one. We had discussed previously the impact that outliers have in OLS regression analysis. I now want to talk about some diagnostic plots that we can use for detecting outliers in our data. One approach that we can use is Cook's distance, or Cook's D, and it's used to estimate the influence of a data point while performing OLS. Studentized residuals is a quotient resulting from the division of a residual by an estimate of its standard deviation. The Bonferroni method is a simple method that allows many comparison statements to be made or confidence intervals to be constructed while still assuring an overall confidence coefficient is maintained. The hat values represent the predicted y values plotted against the actual y values. So the diagnostic plots that we're seeing on the right-hand side all come out of the R computing language. And there's a very simple diagnostic summary test that shows us the results of this, and we can label specific data points as outliers depending on certain thresholds for each one of these metrics. So when we're trying to understand outliers, we don't just have to look at scatter plots and try to visually identify points. We have a wealth of statistical tests available at our disposal that help in detecting outliers. I now want to talk about interaction terms in a model. Adding interaction terms to a regression model can greatly expand our understanding of the relationships among the variables in the model, and it allows for more hypotheses to be tested. Take the following example. I have an equation where I'm trying to understand height, from bacteria and sun. In this case, the height is the height of a shrub in centimeters. I have bacteria, which is the amount of bacteria in the soil, which is 1,000 per milliliter. And I have a variable for sun, which is a dichotomous variable. It's sun is equal to 0 for partial sun, and sun is equal to 1 for full sun. Okay? And an interaction term is essentially looking at our independent variables against each other in the context of our regression model. It will be useful to add an interaction term to the model if we wanted to test the hypothesis that the relationship between the amount of bacteria in the soil on the height of the shrub was different in full sun than in partial sun, which is a very reasonable test to go about. One possibility is that in full sun, plants with more bacteria in the soil tend to be taller, whereas in partial sun, plants with more bacteria in the soil are shorter. Another possibility is that plants with more bacteria in the soil tend to be taller in both full and partial sun, but that the relationship is much more dramatic in full than in partial sun. The presence of a significant interaction indicates that the effect of one predictor variable on the response variable is different at different values of the other predictor variable. It is tested by adding a term to the model in which the two predictor variables are multiplied. So our regression equation will look something like this. I have my height equals beta naught plus beta 1 times bacteria plus beta 2 times sun plus beta 3 times, and here's our interaction term, bacteria times sun. So I'm going to keep the regression equation front and center, so as we're going through the next set of points in the presentation, we can follow along and refer back. Adding an interaction term to a model drastically changes the interpretation of all of the coefficients. If there was no interaction term, beta 1 would have been interpreted as the unique effect of bacteria on height, controlling for sun. But the interaction means that the effect of bacteria on height is different for different values of the sun. So the unique effect of bacteria on height is not limited to beta 1, but also depends on the values of beta 3 and sun. And this is kind of a tricky concept to grasp, so if you're going to use interaction terms, just pay close attention here. The unique effect of bacteria is represented by everything that is multiplied by bacteria in the model. So beta 1 plus beta 3 times sun, beta 1 is now interpreted as the unique effect of bacteria on height only when sun is equal to 0. In our example, once we added the interaction term, our model looks like the following. Adding the interaction term changed the values of beta 1 and beta naught compared to our original model, and this is completely expected. The effect of bacteria on height is now 4.2 plus 3.2 times sun. For plants in partial sun, sun equaling 0, so the effect of bacteria is 4.2 plus 3.2 times 0, which in turn equals 4.2. This means, so for two plants in partial sun, a plant with 1,000 more bacteria per milliliter in the soil would be expected to be 4.2 centimeters taller than a plant with less bacteria. For plants in full sun, however, the effect of bacteria is 4.2 plus 3.2 times 1, which in turn equals 7.4. So for two plants in full sun, a plant with 1,000 more bacteria per milliliter in the soil would be expected to be 7.4 centimeters taller than a plant with less bacteria. Because of this interaction, the effects of having more bacteria in the soil is different if a plant is in full or partial sun, and we see that through the math. Another way of saying this is that the slopes of the regression lines between height and bacteria count are different for different categories of the sun. Beta 3 indicates how different these slopes really are. Interpreting beta 2 is a little more difficult. Beta 2 is the effect of sun when bacteria equals 0. Since bacteria is a continuous variable, it is unlikely that it equals 0 often, if ever. So beta 2 can be virtually meaningless by itself. Instead, it is more useful to understand the effect of sun, but again, this can be difficult. The effect of sun is beta 2 plus beta 3 times bacteria, which is different at every one of the infinite values of bacteria. For that reason, often the only way to get an intuitive understanding of the effect of sun is to plug in a few values of bacteria into an equation and see how height, the response variable, changes. Now that we've talked about interaction variables, OLS regression, gone through some of the diagnostics, I want to touch upon some applications of regression that apply to econometrics and can be used in business applications that are important to understand, and of which we're going to talk about log transformations and interpretations. The presentation so far has really only considered the following form of a linear regression equation. Okay, and this is our simple regression equation from earlier. This is also considered what is called a level-level specification because the raw values of y are being regressed against raw values of x. In this example, how do we interpret what beta 1 is representing? Well, if we differentiate x1 to find the marginal effect of x on y, in this case, beta is the marginal effect. A log-level regression specification is a little different. It's called a log-level specification because we're now taking the logarithm of y and then keeping all of the other variables constant. So it's called log-level because the natural log transformed values of y are being regressed on the raw values of x. We might want to run this particular form of a linear regression model if we think that increases in x lead to a constant percentage increase in y. Some examples would be wage on education, forest lumber volume on years. So instead of an absolute number for forest lumber, maybe it's a percentage growth over time. When our log-level transformation, how do we interpret beta 1? First, we can solve for y, and then we differentiate to get the marginal effect. So in this case, the marginal effect depends on the value of y, with beta itself representing the growth rate. For example, if we estimate that beta 1 is 0.04, we should say that for another year increases the volume of lumber by 4%. A log-log regression specification is taking the log of the dependent variable and the log of the independent variable. This is called a log-log specification because the natural log transform values of y are being regressed on the log transformed values of x. We might want to consider running this specification if we think that percentage increases in x lead to a constant percentage change in y. This is constant demand elasticity, or this is an elasticity function, essentially. So to calculate the marginal effects, we solve for y. And then we differentiate x. From the previous slide, the marginal effect can be represented as follows. And when we solve for beta 1, we get the following. And this implies that beta 1 is an elasticity. So if x1 is a price and y is a demand of a good, and we estimate beta 1 to be equal to minus 0.6, this means that a 1% increase in the price of a good would lead to a 6% decrease in demand. We spent a very large portion of the presentation talking about linear regression concepts. I now want to shift gears and talk about ANOVA. Analysis of the variance, or ANOVA, is used to compare differences of means among two or more groups. It does this by looking at variation in the data and where that variation is found, hence its name. Specifically, ANOVA compares the amount of variation between groups with the amount of variation within groups. It can be used for both observational and experimental studies. When we take samples from a population, we expect each sample mean to differ simply because we're taking a sample rather than measuring the whole population. This is called sampling error, but is often referred to more informally as the effects of chance. Thus, we always expect there to be some differences in means amongst different groups. The question is the difference among groups greater than that expected to be caused solely by chance? In other words, is there likely to be a true, real difference in the population mean? Mathematically, ANOVA can be written as where x are the individual data points, I and j denote the group and the individual observation. The e is the unexplained variation, and the parameters of the model u, mu, are the population means of each group. Thus, each data point is its group's mean plus its error. Some key assumptions of ANOVA when working with the technique is that the response is normally distributed. The variance is similar within different groups, and that the data points themselves are independent. Now we'll get into some hypothesis testing. Like other classical statistical tests, we use ANOVA to calculate a test statistic, which is called the F ratio, with which we can obtain the probability, the p-value, of obtaining the data assuming the null hypothesis. And the null hypothesis, in this case, are all population means are equal, compared to the alternative hypothesis is at least one population mean is different from the rest. A significant p-value, usually taken as a probability less than 0.05, suggests that at least one group mean is significantly different from the others. In other words, a variable with a p-value of 0.05 or less allows for us to consider including the variable within a predictive model. ANOVA separates the variation in the dataset into two parts, between group and within group. These variations are called the sum of squares, which can be seen in the following slides. First, we're going to perform a calculation of the F ratio. The first step is determining the variation between groups. The between group variation, or between group sum of squares, or SS, is calculated by comparing the mean of each group with the overall mean of the data. Specifically, this is the following. We then divide the between sum of squares by the number of degrees of freedom. This is like sample size, except it is n minus 1, because the deviations must sum to 0, and once you know n minus 1, the last one is also known, to get our estimate of the mean variation between groups. The second step of the ANOVA process is talking about the variation within the groups. The within group variation, or the within group sums of squares, is the variation of each observation from its group mean. By adding up the variance of each group times by the degrees of freedom of each group, note, you might also come across the total sum of squares. Within sum of squares is the total sum of squares minus between the sum of squares. As before, we then divide by the total degrees of freedom to get the mean variation within groups. The next step of our ANOVA process is the calculation of the F ratio. The F ratio is then calculated as the mean between group sum of squares divided by the mean within group sum of squares. If the average difference between groups is similar to that within groups, the F ratio is about 1. As the average difference between groups becomes greater than that within groups, the F ratio becomes larger than 1. Therefore, variables with higher F ratio values provide greater explanatory power when utilized in predictive models. To obtain the p-value, it can be tested against the F distribution of a random variable with the degrees of freedom associated with the numerator and denominator of the ratio. The p-value is the probability of getting that F ratio or a greater one. Larger F ratios give smaller p-values. So what we're looking for with the ANOVA test are large F values, or F ratio values. So that's a lot of statistical theory. I mean, it's hard for me to keep up with it, and it's, to keep the focus on it. I just want to talk about ANOVA in a practical sense. Do you prefer ketchup or soy sauce? A very simple question. Well, I guess it depends. If somebody asks you this question, your answer would likely depend on what you're eating. You probably wouldn't dunk your spicy tuna roll in ketchup, and most people probably wouldn't eat soy sauce with hot French fries. A common error when using ANOVA to assess variables is the following. So we collect data about our variables of interest, and now we're ready to do our analysis. This is where many people make the unfortunate mistake of looking only at each variables individually. In addition to considering how each variable impacts your response variable, you also need to evaluate the interaction between those variables and determine if any of those are significant as well. And much like our preference for ketchup versus soy sauce depends on what we're eating, optimum settings for a given variable will depend upon the settings of another variable when an interaction is present. Well, how do we evaluate and interpret an interaction? Let's use a weight loss example to illustrate how we can evaluate an interaction between factors. We're evaluating 2 different diets and 2 different exercise programs. One exercise program is going to focus on cardio, and another exercise program is going to focus on weight training. We want to determine which one results in a greater weight loss. So we randomly assign participants to diet A or diet B in either the cardio or weight training regimen, and then we record the amount of weight that they've lost after a certain period of time, in this case 1 month. So here's a snapshot of the data that we have in our data set. It's a very, very simple one. It's just 3 columns of information, cardio, diet A, and the amount of weight loss. We want to understand how to explain the weight loss variable from the diet variable. So we can do this through the analysis of variance table. And when we run this specification in the R language or your statistical package of choice, we get an output that looks like this. Okay. Another way to think of it is, instead of looking at the between group and within group, think the between group as the diet variable and then the within group as the residuals. Okay. Now, some observations that I have is that the f value, or f ratio, is well over 1, which indicates that this variable has some explanatory value for weight loss. And the p-value is statistically significant at the 0.05 level. Let's take a look at the ANOVA output for both the diet and exercise variables. So now I'm increasing the amount of variables that I'm performing my ANOVA on. So diet and exercise are now both the between group. My residuals are still my within group. And some observations that we can note here is that the diet variable has an f value of 13.69, which is well over 1. The exercise variable has an f value of 6.355. And both variables are statistically significant at the 0.05 level. Now we're going to do a third variant, which is looking at diet, exercise, and an interaction term of diet and exercise together. We can see that the p-value for the exercise and diet interaction term is very close to 0. Okay, because this p-value is so small, we can conclude that there is indeed a significant interaction between exercise and diet. So which diet is better? Our data suggests it's like asking the question, okay, well, ketchup or soy sauce? Well, the answer is, well, it depends. Since the exercise-diet interaction is significant, let's use an interaction plot to take a closer look. So here's an interaction plot of diet and weight loss. For participants using the cardio program, which is shown in black, we can see that diet A is best and results in greater weight loss. However, if you're following the weight training regimen, shown in red, then diet B results in greater weight loss than diet A. Suppose this interaction wasn't on our radar, and we instead focused only on individual main effects and their impact on weight loss. Based on this plot that we have in front, we would incorrectly conclude that diet A is better than diet B. As we saw from the interaction plot, that is only true if we're looking at the cardio group. Clearly, we always need to evaluate interactions when analyzing multiple factors. If you don't, you run the risk of drawing incorrect conclusions, and you might just get ketchup with your sushi roll. And ANOVA is an incredible tool that we can use to help aid in assessing interaction terms. ANOVA can also be used as a means to compare two linear regression models using the chi-square measure. Okay, so ANOVA is even more flexible that not just individual variables we can compare, but we can actually compare specifications of models. Here are two regression models we want to compare to each other. The order here is important, so make sure that you're applying the correct selection of the models. So when I run my analysis of the variance, I get the following output. The p-value of the test is 0.82. It means that the fitted model, Model 1, is not significantly different from Model 2 at the level of alpha equals 0.05. Note that this test makes sense only if Model 1 and Model 2 are nested models, which is it tests whether reduction in the residual sum of squares are statistically significant or not. So we spent a lot of time talking about ANOVA and linear regression. Linear regression is used to analyze continuous relationships. However, regression is essentially the same as ANOVA. This is really a powerful aha moment that I've had, is that there are two sides of the same coin. In ANOVA, we calculate means and deviations of our data from the means. In linear regression, we calculate the best line through the data and calculate the deviations of the data from this line. The F ratio can be calculated in both circumstances. Now that we've talked about linear regression analysis and ANOVA concepts, I want to shift gears and go back to a practical application of predictive analytics. I want to talk about an example using the Boston housing market. Before we begin any type of analysis, it's always paramount to understand the data that we're working with. The dynamics and rapid change of the real estate market requires business decision makers to seek advanced analytical solutions to maintain a competitive edge. Real estate pricing and home valuation can greatly benefit from predictive modeling techniques, in particular linear regression. The dataset we'll be working with reviews home values in Boston, Massachusetts, and compiles a number of other statistics to help aid in determining property value. Our goal for this exercise will be to provide a predictive model that can be leveraged to help real estate businesses in the Boston market. Here is a description of the variables within the dataset. Now, most housing datasets, when we're thinking of the price of a home, number of bathrooms, square foot, amenities, and so on and so forth. This dataset is a little different. We could expand the analysis and bring those considerations in, but that's not necessarily the goal of this assessment. So the variables that we have, we understand crime rates, so the per capita crime rates by a particular town. We understand the proportion of land zoned for lots of a certain size. We know how much non-retail businesses are in the town. We have an indicator variable concerning a river, whether or not if you're close to the river or not close to the river. We understand some pollution components, and then some characteristics of the actual houses themselves. So, the number of rooms per dwelling. We understand an age variable, and so on and so forth. But the variable of interest for us is understanding the median value of owner-occupied homes, which is represented in thousands. So the MEDV variable is the variable of interest. So our goal is going to be to develop a multiple linear regression model for this median value of a home based on these other variables. I always like to take a look at the raw data before I go about my modeling. This is where we would go through extensive EDA and data munging processes. We're not going to go through that here because we want to focus on the application of the technique, but it's always a good sense to just get a sense of what kind of data we're looking at here. And things that pop out to me immediately are that we're looking at all numeric values, and at a tertiary glance appears to be in good working order. So with so many potential independent variables, we need to reduce the field of variables to only those which can help to explain the model. There are many ways that we can go about this. We can review the correlation matrix, and when we review this matrix, we see a number of variables which we can use to help build the model. In particular, we're looking for correlations that are closer to 1 or -1. Based upon the correlations, we will initially focus on utilizing the following variables: indus, RM, tax, PT ratio, and LSTAT. Now there are many other techniques that we can go about using this, but I want to show how we can go about just building an initial model. Afterwards, we're going to assess the quality of this model's approach, and then we're going to utilize an alternative modeling approach. So, is using correlation the right way to build a model or not? Can we come up with something better? I don't know. I guess we'll see. So reviewing the model's output shows a couple of potential issues with the model. Despite having a correlation of minus 0.484 to the median value, the industry variable is not statistically significant. We see this by the p-value of being 0.2802 and should be dropped from the model. The tax variable is also statistically insignificant and should be removed from the model. The adjusted R-squared is 0.6772, which indicates a reasonable goodness of fit, and 67.7% of the variation in house prices can be explained by these 5 variables. So 67.7% is actually a very good R-squared value. There are some individuals who would argue, based off of industry experience and their knowledge in working in business, that we can leave this model as is, and that the model performs reasonably well. Nevertheless, we will rebuild this model and we'll try to improve its performance. Let's double check that the dependent variable is normally distributed. It appears that the dataset is left skewed and could benefit from a log transformation. So we'll go ahead and we'll perform the transformation. Let's utilize an automated feature selection procedure called stepwise selection. And if you're unfamiliar with this technique, I cover it in detail in the EDA presentation prior to this one. Okay, and we're going to use this technique to identify those variables which are both statistically significant and add value to the regression model. So we start with all the variables in, with our dependent variable now being our log median value. And after the stepwise procedure has completed, we now see that all of our variables are significant at the p equals 0.05 level. And this is because I specified in the selection procedure that I only want variables that are significant at this level. So I calibrated my model to better suit my needs. Additionally, the model now has an adjusted R-squared of 73.4% compared to 67.7%, which is a notable improvement. So not only do I have statistically significant coefficients, I have an increase in predictive performance over the previous model. Well, let's check the VIF to determine whether multicollinearity is an issue. We can see in this case that all of the values are below 3, which indicates that this is not an issue. Remember, we talked about different threshold levels. I decided to be a little more stringent in this case and use 3 instead of 5. A review of the quantile-quantile plot indicates that the data generally agrees with a normal distribution. However, there are longer tails at the ends of the distribution. A review of the residual plot indicates the potential need to apply some transformation of the independent variable to further improve the model. Okay. And looking at the spread of the residuals, we can see that there is a pattern that emerges on the right-hand side. There is some fanning out. It's not completely randomly spread across the chart. Okay. Nevertheless, this is the model that we're going to use. Okay, so if we wanted to continue to tweak the parameters, we could go about doing this. So the final model that we have shows the log of price equaling 2.8 plus 0.12 times rooms minus 0.03 times income minus 0.01 times crime plus 0.01 times zone plus 0.13 times river minus 0.3 times employee. When we performed a log level transformation of this data, we now have to interpret the model as a change in x as a constant percentage increase in y. Okay, so we're not looking at level because of that log transformation. So an interpretation of what these parameter estimates mean, we can think of each additional room a house has leads to an increase of price by 12%, holding other variables constant. And that's what that room variable is indicating. Okay, so if I have more rooms in a house, my price is going to go up by 12%. If the home is near the river, the price increases by 13%, holding the other variables constant. Okay, so riverfront property is prime real estate in the Boston market. When a house is close to the main employment centers, the price decreases by 3% per unit. And this, to me, is a very interesting phenomenon to understand. So if I'm closer to big businesses, my home value actually is less. And that could be because of, noise, pollution, the smell, and that makes intuitive sense. But what is great about this model is now we're able to quantify the relationship between price and these various factors. Okay, and this is a great application of using regression analysis, performing some transformations, drawing from different techniques that kind of showcase the power of OLS. I now want to take the time to get into a more in-depth example that touches on building off of regression analysis, and we'll even get into some simple optimization. Before we begin, it's always important to understand the data in the context that we're working within. In this case, we have a supermarket that is selling a new type of grape juice in some of its stores for a pilot test. The senior management wants to understand the relationship between the grape juice and how it's going to impact apple juice, cookie sales, and overall profitability. This is a very fair question. So I'm going to introduce a new product in a business sense, and I want to know, am I going to cannibalize my sales? And how can I better understand that? And what's the impact going to be on profitability, and so on and so forth. We will showcase how it's possible to build off of linear OLS regression models and econometric methodologies to solve a series of advanced business problems. The goal will be to provide tangible recommendations from our analyses to help the business manage their portfolio. Our goal is to set up an experiment or a series of experiments to analyze the following. Which type of in-store advertisements are more effective? The marketing group has placed two types of ads in stores for testing, which is referred to as A/B testing. So they have one theme of the advertisement is looking at a natural production of the juice, and the other theme is looking at a family health setting. We want to develop an experiment to understand price elasticity, reactions of the sales quantity of the grape juice to its price change. We want to understand the cross-price elasticity, reactions of sales quantity of the grape juice to the price changes of other products such as apple juice and cookies in the same store. And we also want to find what the best unit price of the grape juice is, where we can maximize the profit and forecast the sales with that price. So we want to try to optimize our pricing, based off of a series of constraints. First, let's take a look at the raw data in the table. And I spend a lot of time understanding the structure of the data, because if we want to replicate this type of analysis in future ways, just look at how the data is constructed. Here is a description of the variables within the data set. So sales in this case is the total unit sales of the grape juice in 1 week in the store. The price is the average unit price of the grape juice in the week. Ad type is a binary indicator variable, with 0 representing the theme of the ad is the natural production of the juice, And if it's a 1, the theme of the ad is representing the family health caring ad. Then we have the price of apple and the price of cookies. And both of these are the average unit price of the apple juice in the store in a week and the average unit price of cookies in the same store in that week. Now, each observation, each line is representing a different point of data. So every week we see that the supermarket is evolving their pricing. So because of this, we have enough data where we can start to really kind of dig into the elasticity portions of that. And that's just one thing to consider when looking at applying this data to other types of business problems. One important aspect is to create some summary statistics, and we'll draw from these summary statistics later on in the example. But a simple summary shows that the mean value of sales of grape juice is 216.7 units, and the minimum value is 131, and the max value is 335. We can further explore the distribution of the data of sales by visualizing the data in graphical form as follows. So this is where our extensive EDA techniques will come into play, but just doing a very simple view of the data, we don't find any outliers in the box plot graph, and the sales distribution is roughly normal. I don't think it's necessary to apply any further data cleaning and treatment to the data set to go about and begin building models. So our supermarket marketing team wants to find out the ad that has better effectiveness for sales between the two different types of the ads. So remember, we had our natural production theme advertising campaign that's going on in a supermarket store. And then we have a different theme, which is the family health caring theme. To find out which is the better ad, we can calculate and compare the mean of sales with the two different ad types at the first step. The mean of sales with a natural product theme is about 187, and the mean of sales with the family health caring theme is about 247. Now I know I'm simplifying this approach. There are other variables and characteristics that are important in understanding, why the sales have developed in one way or the other. But I think in terms of making a simple comparison, this proves the point. But in an actual business setting, we'd have to dig a little deeper. And it looks like the latter one is better. Okay. So in this case, from our A/B testing, we're seeing that the family health caring theme produces better sales results, all things being equal. To find out how likely the conclusion is correct for the entire population, it's necessary to do some statistical testing. And in this case, we're going to do some two-sample t-tests. We can see that both data sets are normally distributed, and to be certain, we can run the Shapiro-Wilk test. The p-values of the Shapiro-Wilk test are larger than 0.05, so there is no strong evidence to reject the null hypothesis that the two groups of sales data are normally distributed. Now we can conduct the Welch two-sample t-test since the t-test assumptions have been met. From the output of this test, we have strong evidence to say that the population means of the sales with the two different ad types are different because the p-value of the t-test is very small. With 95% confidence, we can estimate that the mean of the sales with natural production theme ad is somewhere in between 27 to 93 units less than that of the sales with the family health caring theme ad. So we really didn't talk about t-tests too much, or the Welch test, but understand that this is a test that we can use to corroborate our findings. So the conclusion is that the ad with the theme of family health caring is in fact better. Now we're going to spend some time talking about sales driver and price elasticity analysis. With the information given in the data set, we can explore how grape juice price, ad type, apple juice price, cookies price influence the sales of grape juice price in a store by multiple linear regression analysis. Here, sales is the dependent variable and the others are the independent variables. First, let's investigate the correlation between the sales and other variables by displaying the correlation coefficients in pairs. And so the graph I have on the right-hand side is just another type of scatter plot matrix that contains a bunch of information. The correlation coefficients between sales and price, ad type, price apple, and price cookies are 0.85, 0.58, 0.37, and 0.37 respectively. That means that they all might have some influence on the sales. So the correlations aren't terribly low. In some cases, we have some very high correlations as well. We can try to add all of these independent variables into a regression model. When we do this, the p-value for price, ad type, and price of cookies is much less than 0.05. They are statistically significant in explaining the sales. We're confident to include these variables in our model. The p-value of the price of apple juice is a bit larger than 0.05. We see it's a 0.08. And that seems that there's no strong statistical evidence for apple juice price to explain the sales. However, according to our real-life experience, we know that when apple juice price is lower, consumers are likely to buy more apple juice, and then the sales of other fruit juice will decrease. So this is an example where having subject matter expertise is outweighing our statistical assumptions. Okay, so if I lower the price of fruit juice, there's a very good chance that people are going to buy more of that fruit juice, and it will impact the sales of the other fruit juice. It's a very reasonable assumption to make. So we're going to add this component to the model to help to explain the grape juice sales, despite it not being statistically significant. The adjusted R-squared of this model is 0.881, which indicates a reasonable goodness of fit, and that 88% of the variation's sales can be explained by these four variables. So we have an R-squared of 0.88, which is a very high R-squared, and I'm glad to see that. We have a very strong model here. The assumptions for the regression to be true are that the data are random and independent, residuals are normally distributed, and have constant variance. Let's check that the residual assumptions visually. The residuals versus fitted graph above shows that the residuals scatter around the fitted line with no obvious pattern, and the normal quantile graph shows that basically the residuals are normally distributed. The assumptions are met in this case. So I don't think we have any gross violations of OLS assumptions. So we can go ahead and move forward. If we perform the VIF test, we see that each value is relatively close to 1, which indicates that multicollinearity is very low amongst these variables, which is great. Now that we've properly vetted our linear regression model, we can describe it as following. Okay, so sales is equal to 774.81 minus 51.24 times price plus 29.74 times ad type plus 22.1 times the price of apple minus 25.28 times the price of cookies. With this model established, we can analyze the price elasticity and cross price elasticity to predict the reactions of the sales quantity to price. Okay, so for price elasticity, which essentially is the change in quantity over the change of the price, we're able to calculate it as follows. So P represents price, Q represents the sales quantity. The change in quantity over change in price is minus 51.24, which is the parameter before the variable price in the above model. Price divided by Q is 9.738 divided by 216.7, which is 0.045. The P in this equation is the average price of the data set. So if we went back and looked at our summary statistics, we'll find that the average price of grape juice is 9.738. Okay, and Q is the average price or the average value of the sales quantity variable. So from this, we've calculated our price elasticity, and the interpretation is that a 10% decrease in the grape juice price will increase the grape juice sales by 23% and vice versa. So we now have a quantifiable relationship of the elasticity and its impact on demand versus change of price. We can further calculate the cross-price elasticity on apple juice and cookies to analyze how the change of apple juice price and cookie price influences the sales of grape juice. So we first calculate the cross-price elasticity for the apple juice. Then we calculate the cross-price elasticity for cookies. And we can interpret that for the cross-price elasticity for apple is that a 10% decrease in apple juice price will decrease the sales of grape juice by 7.8% and vice versa. So this is telling us in a business sense that the grape juice and apple juice are substitute products. Likewise, the cross-price elasticity of cookies indicates that 10% decrease in a cookie price will increase the grape juice sales by 11.2% and vice versa. So the grape juice and cookies are complementary products. If we place these two products together, we'll likely increase the sales for both of them. So if people are buying cookies and grape juice together and we see this relationship in the data, we can use this to refine our strategy in terms of product placement throughout the supermarket. Okay, and we can also know that the grape juice sales increase 29.74 units when using the ad with the family health caring theme. So the health caring theme advertising campaign led to an increase of sales significantly. Usually, companies want to get higher profit than just higher sales quantity. So the question is, how do we set the optimal price for new grape juice to get the maximum profit based on our data set in our pilot period and our regression model? How do we draw from this regression analysis to optimize the price? To simplify this question, which can be a very complicated question, I want to impose some parameters and some constraints to the model. In this case, we're only going to look at ad type of 1, and we're going to assume that the price of apple is going to be 7.66, which is the mean value. The price of cookies is going to be 9.74, which is the mean value. So if I take my linear regression model and I plug in the numbers that we have up here, I get a simplified model that says 772.64 minus 51.24 times price. Now that we've run our optimization function, we've determined that the optimal price is $10.04, and this is the price that gives us the maximum profit, in this case, meaning $1,300.01. In reality, we can take this $10.04 price and we can set the price to be $10, or if we want to get fancy with our marketing, $9.99. We can further use the model to predict the sales when the price is at $10. So I'm going to use the same constraints that we had earlier. I'm going to say that the family caring ad campaign is the campaign that we're going to be using moving forward. I'm going to take the mean price of my apple juice and my mean price of my cookies, apple juice being $7.66, the mean price of cookies being $9.74, and I'm going to plug it into our multiple linear regression model we had produced earlier. When I do this, I get the result that the sales forecast will be 215 units with a standard error in a variable range of 176 to 254 units at the 95% confidence interval level. And this is for a single store in 1 week on average. Based on this forecast and other factors, the supermarket can now begin to prepare the inventory for all of its stores after the pilot period. So we've introduced the concept of bringing in a new product, some A/B testing to see which one of the products is superior to the other, and now we're going to launch this at a macro scale. How can we go about preparing our distribution network to have the right inventory on hand that makes sense off of the data that we've seen? Additionally, we were able to leverage price elasticity and cross-price elasticity to find ways to put products closer together to each other to maximize their sales effect, understand the relationship of that effect, and even answer some of our senior management's concerns about optimizing the price, all within the context of this example. And what's so great about it is that the root of it is using OLS regression to drive the entire point home.